Welcome back to the Game of Drones. I'm still Hal Cowan, and today I'll be joined by Rafael Bieber, who has extensively written about the current conflict in Ukraine and its prolific use of drones. He will focus on the developments that have increased the efficacy of drone warfare and the adaptations that have been made to counter drone defences, as described in the last episode. Over to you, Raf.
Thank you, Hal. The war in Ukraine is a conflict that began with the Russian annexation of Crimea and part of the Donbass in 2014, before escalating into a full-scale invasion in 2022. It has been characterized by the extensive and evolving employment of many types of unmanned aerial vehicles by both sides. In the early stages of the conflict, drones were primarily used for reconnaissance, battlefield surveillance, and artillery spotting. UAVs were also employed in the OSCE Special Monitoring Mission to track ceasefire infringements and monitor movement of heavy weapons. In October 2021, shortly before the full-scale invasion, Ukraine conducted its first combat strike using the Bayraktar TP2 drone against separatist artillery positions. This marked a significant shift in priorities from primarily sensor-based drones to strike platforms. In the early weeks of the full-scale invasion, these drones inflicted notable losses on Russian armoured columns headed towards Kiev. This highlighted the vulnerabilities of traditional military tactics to modern drone warfare. The dominance of the Bayraktar, however, was short-lived. As the initial chaos of the invasion subsided, the proliferation of Russian electronic warfare systems and the adaptations of short-range air defense, SHORAD, to target smaller UAV-sized targets significantly increased the attrition rates, forcing TB2 operations further from the front line. The next major milestone came with the introduction of FPV technology. As neither sides were able to establish or maintain air superiority over the battlefield, access to precision strike capabilities were limited, often relying on artillery which was slow and less reactive or expensive missile systems. FPV kamikaze drones filled this gap, providing a cheap, reliable, and effective counter to armour and personnel. These could easily be operated by soldiers close to the front line with minimal training. Throughout the war, both sides have continued to adapt these systems to make them cheaper, more reliable, and harder to counter. Anti-jamming and electronic countermeasures. By 2024, electronic warfare became one of the most dominant causes of drone losses, with the majority, up to 75% of both sides' drones neutralized through jamming, GPS spoofing, or link disruption. This attrition forced rapid adaptation that led to increasingly sophisticated electronic countermeasures. Most commercial drones rely on control and bi-directional telemetry links operating in relatively narrow frequency bands. These signals are easily jammed. High power interference is transmitted to certain frequency bands, which easily collapses the signal-to-noise ratio at the receiver. Simply increasing transmitted power is rarely an applicable solution, due to power constraints and diminishing returns in contested electromagnetic environments. One solution many systems adopted are spread spectrum transmission techniques. The signal is distributed across a large portion of the electromagnetic spectrum. This changes the economics of jamming. An adversary must invest significant capital and energy to jam entire bands or accept the decreasing effectiveness of their jamming networks. Wideband jamming is energy intensive and increases the risks of detection of jammers and subsequent destruction, making spread spectrum an asymmetric and economically efficient countermeasure. One commonly used technique is frequency hopping, in which the carrier frequency changes many times a second according to a predetermined pattern, which is shared between the operator and the receiver. To an outsider observer with no knowledge of the hopping sequence, the signal is difficult to track, intercept, or jam. Importantly, this method is relatively cheap to implement, as common commercial radio chipsets can easily be adapted to this method. Another approach that is extensively used is direct sequence spread, or DSSS. In this method, the transmitted signal is multiplied by a pseudo-random binary sequence. The signal's energy is spread over a wide frequency band, while the total transmitted power remains unchanged. the individual power at each frequency is significantly reduced, giving it the appearance of noise for outside observers. At the receiver, the same pseudo-random code is used to correlate the incoming signals, recovering the desired transmission while rejecting noise and jamming. Early in the war, DSSS proved particularly effective against Russian electronic warfare systems as they were optimized to counter narrow band control links. While on paper the jammers worked, Ukrainian drones employing DSSS were able to penetrate Russian electronic warfare. This offensive-defensive mismatch prompted the development of more adaptive electronic warfare and the proliferation of kinetic countermeasures. The most effective way to counteract jamming entirely is by eliminating radio control links in their entirety. First deployed by the Russians in the spring of 2024, drones equipped with large fiber optic spools effectively overcame heavy electronic jamming deployed by the Ukrainians. These fiber optic drones offered low latency and are harder to electromagnetically detect than regular radio-controlled counterparts. However, these systems come with significant disadvantages to their offensive capabilities. The added weight of the fiber spool leads to lower payload than comparable non-fiber optic drones and means they are less maneuverable. It has also been reported that sourcing significant quantities of high enough quality fiber optics has been difficult and expensive, which has constrained their use. Industrializing drone warfare. In the current conflict, drone warfare has developed not just through technological innovations, but through a fundamental shift in the way unmanned systems are produced. Rather than relying on a limited number of high-end systems, both sides have moved towards the large-scale proliferation of low-cost and expandable drones. This shift has been driven by emphasis on rapid, distributed manufacturing. Civilian supply chains, volunteer groups, and small commercial workshops have been leveraged to expedite production and reduce costs. To facilitate the rapid assembly, new models of drones that replace expensive materials and advanced technologies with off-the-shelf components and 3D printing have been made. By distributing production over wider areas and reducing reliance on specialized, expensive, heavy equipment, supply chains are strengthened and the damage caused by attacks are limited. These new systems are designed with attrition in mind. Instead of prioritizing durability and survivability, these drones are built with the idea of a short service life, sometimes only a single mission in the case of kamikaze drones, which have become prolific in the conflict. Mass production has also shortened the adaptation cycle. Adaptations and improvisations from the front line can be quickly incorporated into new designs and fielded in a matter of weeks, not years. As a result, defences can be quickly overcome and even rendered obsolete. In these circumstances, the factory floor and logistical networks can be as strategically important as the front line itself. Stealth drones. One of the most effective ways to increase a drone's survivability is to reduce the likelihood of its detection before it reaches the target. One of the most detectable signatures of any UAV is its acoustic footprint, which is dominated by the noise generated from propellers during flight. As the propeller rotates through the air, regions of high pressure form on the blade's leading edge, while regions of low pressure form behind it. The resulting periodic fluctuations of pressure propagate outwards in the form of sound waves. Additional noise arises from aerodynamic turbulence, especially from the formation of vertices at the blade's tips, as well as structural effects, such as the flexing of blades and their oscillations. Several adaptations in blade designs can be made to mitigate these effects. To reduce tip noise, the tips of the blades can be swept back, which spreads the pressure change over a longer time interval and weakens the reducing vortices. The geometry of the blades may also be optimized. By reducing the thickness of the blades and adding leading edges, flow separation and turbulent wakes can be minimized. Noise reduction can also be achieved by the optimization of chord length and twist distribution along the blade. Propellers are typically wider at their hub and then taper towards the tip, with twists through the whole length. This maintains an optimal angle of attack along the blade, thereby reducing turbulent flow and so reducing the noise profile of the drone. Other adaptations include serrated trailing edges, inspired by the wings of owls, that break up the coherent vortices into smaller, weaker eddies, thereby reducing their acoustic signature. Advances in material science allow the use of thin, stiff carbon fiber composite blades, reducing blade flex and vibrations while also improving their aerodynamic efficiency. Civilian adaptations. Many of the adaptations and developments driven by the battlefield requirements of the war in Ukraine have clear and beneficial adaptations to civilian sectors. Technologies that have made drones cheaper, more versatile, and ensured reliability in complex and hazardous situations translate effectively into the civilian environments. In disaster relief, such as the 2023 earthquakes in Turkey and Syria, drones designed to operate in heavy interference environments, equipped with thermal imaging sensors, have been used to locate survivors and assess structural damage in areas that are hazardous to human responders. The reduction in unit cost and move towards mass production has also increased the accessibility to drones. As a result, they can be deployed at scale to counter labour shortages by automating heavy labour tasks such as crop dusting. This improves efficiency and scale while reducing her human workload. Finally, the acoustic stealth adaptations, specifically low noise propeller design, enables drones to be used for wildlife monitoring with minimal disturbance to the natural ecosystem. Much like many technologies that have been developed through warfare, drones have many commercial applications and have the potential to deliver significant benefits outside the battlefield. In conclusion, the war in Ukraine has demonstrated that drone warfare is defined not solely by individual technological breakthroughs, but more by the speed of adaptations, both technical and doctrinal. Unmanned aerial vehicles have evolved from a niche reconnaissance tool into a cornerstone of modern offensive and defensive operations. While conflict has seen the rapid development of many counter-drone defences, the versatility and upgradability of UAVs have allowed them to continuously evolve to meet emerging threats. This continuous cycle of adaptation ensures drones will remain a central feature of modern and future conflicts.
Thank you, Raf, for these insights. In the next episode, we'll cover the use of artificial intelligence in drone fare. It has a profound technical and ethical implication, and so certainly will be an interesting listen. Thank you all for listening, and tune into the next episode.